Welcome again to the NPTEL course on storage systems. In the previous class, we were trying to understand why it is not easy to get a kind of consistency in storage systems. Basically because you have to solve some coordination problems, and these coordination problems have inherent difficulty in the context of failures. So we looked at some of the issues. For example, we briefly looked at the two generals problem. We just looked at the kind of problems that will be there. I just mentioned something about the FLP result, and then the fact that you can't even have reliable communication in the face of crashes. The various interesting results are there, which basically show that there are some problems. We also looked at briefly at the CAP theorem, which basically tells you that certain things are not possible. That is, for example, you can't have consistency, availability, and tolerance to partitions at the same time. Okay. So I also briefly mentioned about the kind of differences that exist between file systems and databases, because file systems usually don't have application level information. So they can only attempt to be consistent at in their own data structures, and whereas database typically has much more information on applications, therefore they can do something better. Okay. So I think we also tried to briefly look at some issues about why in practice also this is very difficult. We gave you I gave some examples of some interesting problems that we come across, okay, in real life. Okay. So basically the issue is that detecting when some system is dead or alive itself is a difficult problem. So it might be that the system is extremely slow, and therefore it is almost indistinguishable from a failure. So the question is, do you wait for that system to show signs of life, or you decide that it's not possible and move on? Okay. Now this is a very tricky issue to be handled. Depending on how you handle this issue, different kinds of models are possible. For example, if your system worries about consistency very carefully because it involves a lot of real world implications, okay. For example, it involves money, etc., then you may want to wait for the system to correct itself. There are some other situations where either it's not important, therefore it's okay to proceed, or you are under real-time pressure, you have to do something right. You don't have all the information, you still have to do something right. For example, if you have an aeroplane tracking system, air controller kind of systems, if some part of the system has failed, that does not stop you from having to do some acts so that the aeroplanes still take off and land smoothly. Okay. Even if there are failures, you still have to proceed somehow. Okay. So because of these different kinds of situations, we'll find different kinds of models. Okay. So we will try to look at some of these issues in some detail. And so today I will talk about the slightly more, let us say, detailed way with respect to these problems. Okay. First thing, I think, as we mentioned before, distributed consensus is not possible. That's basically this is a Fisher-Lynch-Patterson result. It basically shows that distributed consensus is not possible even with one faulty processor. And therefore, if distributed consensus is not possible, distributed locking also is not possible. Because what is locking? Basically, it is you have k number of parties who one of them has to be able to enter the critical section or the area which is the shared region which has to be modified. So if distributed consensus is not possible, that means there is no way to say whether one party can be in that shared region. Okay. It's not possible. Similarly, distributed synchronization is not possible. In many cases, what happens is that multiple parties have to step through certain steps. They have to go through certain steps in a particular order. You want to synchronize the way they execute. So distributed synchronization may also be not possible, because I can always reduce it to the problem of consensus. That is, I want to know whether I am in stage 5 or stage 8 across all the parties who are involved. So this also turns out to be impossible. Okay. So for the same reason, it turns out that if I am trying to do consistency, which is the issue for clustered or distributed file systems or databases, they essentially have to agree on whose value has to be used to update the most recent version of some piece of data. That means they all have to agree. Therefore, in some sense, the commit problem also is connected with this issue. Okay. There are some interesting connections with some other types of work, what is called wait for synchronization, where the idea is to synchronize and in a way which does not prevent you from making progress even in spite of failures. They are somewhat similar. Actually, this result also has some bearing on this particular area, but we will not get into this one. Okay. So what I'm trying to say is that once we have this FLP impossible result, there are a lot of things which get affected by this particular result. So you do have to look at engineering solutions which actually take care of this problem, because in theory it is impossible, but in practice you have to find some way to resolve this problem. Okay. It will be certainly fail in some situation, whatever engineering you do, but that is a fact of life. You have to live with it. Now let's look at just quickly look at the kinds of systems you might come across and what kind of guarantees they give. Okay. For example, it might be distributed locking or synchronization, that is stepping through phases of the program or the computation, or agreeing on a particular value to be committed, etc. Okay. So let's just look at how they are being handled. Before I proceed, I'll just go over the slide we saw some time back. So basically, we have various types of models. We have the POSIX model, the NFS kind of model, the ad hoc model that 1980s people came up with, the Amazon model, which is a more recent one, and Zookeeper also is some fairly recent one. I'm just giving you as 4 examples of the kinds of properties they get. POSIX has certain, it tries to give you some interesting guarantees, and of course the guarantees are finally based on what the devices can give it. Okay. For example, in POSIX you can write something, and unless you verify that what has been written is the same as what you wrote, okay, you are essentially trusting the device to have done it. Now this is might seem trivial, but it turns out that devices do malfunction. You can ask it to write a particular track. It's possible for it to write on some other track. This is what is called off-track writes. That's possible. It's also possible that when you write it, it tells you that it has written successfully, whereas actually it's not written it. That also is possible. This can happen because if you're talking about disk systems, the disks work on the basis of what is called the Bernoulli effect. That is, the disk heads are hovering over the write surface about some few microns above, or actually fractions of a micron above, and if there is any let us say small dust particle, etc., then essentially it goes over it, and when it is writing at that point, it may not succeed in writing with the magnetic strength that is required to write it, because it is no longer at that same few fractions of a micron height. It may be at much higher one. Therefore, the write may not be properly done. That also is possible. So the only solution for, if you want reliability in POSIX kind of models, after writing it, you try to read it. If you read it back, and if it is the same as what you tried, then you know that it's been done. This is basically what is called write verify. Actually, there is a SCSI command which does this, and this is very important because in some situations, especially when it's very cold, it turns out that sometimes there are some problems with the disk and they can actually start malfunctioning. Or if you end up going to some place like Tibet where the air is quite thin, it turns out disks don't work there properly for the same reason. Okay. So if you are thinking that POSIX will give you some guarantees, it's actually dependent on the kind of guarantees that the disk device is giving you. Okay. So that's kind of one kind of device determined kind of guarantees. We looked at NFS. This basically because of reasons of throughput or latencies, you do caching, and because of the caching purposes, it turns out that the value that, if you look at the attributes, it may have a stale value and you might still proceed because it has not timed out. So there are issues of that kind that are there in NFS. If you look at Amazon S3, the problems that are here are because of what we discussed in the previous class, because of FLP or cap related cap. Basically, you can't have consistency, availability, and resilience to partitions at the same time. Okay, that's because of, so this Amazon S3 can give you a much weaker type of consistency model, and that is basically reason why you have to be careful about the model that they provide. Similarly, there is a Zookeeper, which is a hierarchical file-like service, and this one also has a slightly different model. We will actually take a quick look at exactly what it does. So what is S3? S3 is basically key value store, whereas Zookeeper is a, if you are familiar with the proc file system in Linux, it's something similar to that. Okay. So the idea here is you want to provide certain information in a tree-like fashion, and this memory based, and various clients can actually get information about some particular state of the system from this file-like service. Okay. So basically, in some sense, you want to coordinate between multiple users, and they all put their information into a hierarchical kind of model, and it's a memory based system. Okay. It's replicated, and it provides permission to construct more complex services. Synchronization. I mentioned synchronization basically, as I mentioned earlier, you in a distributed problem, it is possible that you want to sequence multiple users through the same steps. That is, all of them have to have been in step 1, then only you can go to step 2, then all of them have to finish whatever they are doing in step 2, then go to step 3. So you want to synchronize those things. Okay. Or you can have issues like group membership. Oftentimes when you are trying to make some value the same in all places, for example consistency, you might want to send messages across. When you are sending messages across, it is important that all the messages be received in all the places in the same order. Sometimes it's very important. Okay. If there are two sets of messages, one modifying A and one modifying B, and some messages that go to certain clients of A get interspersed with messages for updating B, sometimes it can have very peculiar results. So, and this becomes even more complicated when things fail. So there are a whole model called group communication systems, which guarantee how messages are sent and the ordering between messages as received by various clients. Okay. So this is a very tricky area, and it turns out to have some connections with the problems we discussed before, that is FLP result, etc. So this also turns out to be impossible if you make the most general assumptions, but engineering wise you can certainly do something about this also. So as we discussed before, I am not going to go into this before, as we discussed it before. This S3 basically stores data in named buckets. We have some API. So you have a bucket is something like your directory, an object is accessed through a key. So we have seen the this particular API before. Okay. So this is one type of storage. The Zookeeper, as I mentioned earlier, is a tree-based information model. It's like a pseudo file system, just like /proc in Linux. Okay. It's fast and simple. It's based on memory, and each node stores one or more pieces of information. Okay. For example, just like in Linux, if you go to /proc CPU info, it gives you some information about the CPU. So this is also, Zookeeper also does the same thing, except that this is a coordination device. It's basically used so that multiple parties can pick up information and update information, and Zookeeper does that. The important thing is to make sure it is highly available, so it has to be replicated, and if multiple parties try to attempt to update the same piece of information at the same time, then there has to be some ordering by which it happens. Okay. So this has a very simple programming interface. You can create a node at the location tree. For example, if I take again the Linux model, I might have some information called /proc /some x. I can create a node which says /proc x/y, for example. I can delete a node. I can check if a particular node exists at a location. I can get the value or the set value. I can figure out all the things that are there at, for example, /proc x, that there is something called y, z, etc. And or I also have a model which says sync. What does it mean? It means that some changes are taken place. I would like to wait till it all stabilizes. Okay. So essentially, it's like if the model could be something similar to what you have in regular file systems, where you can do what's called fsync, and the idea is that you want to ensure that the values get updated on the disk. So there is a similar procedure they have provided to make sure that you can wait for data to be propagated, and you will get a signal saying that it's done, then only you can proceed. Okay. Now what are the things that they provide? Okay. S3 actually has some model called eventual consistency. What does it stand for? It stands for when no updates occur for a long period of time, eventually all updates will propagate through the system and all the replicas will be consistent. Okay. Notice that it doesn't say how long it is. It just says long enough. Now this of course is a problematic thing, and so essentially it is very closely connected to the kind of system you are thinking about. Okay. It could be a wide area network system, it could be a local area network, and this long period of time depends on that particular aspect. Okay. Actually, ideally it should be, this long period of time should be adaptive. It should be based on a current load on the system. If the load is very high, probably should be longer time. If the load is very light, it should be smaller amount of time. If you look at the time desynchronous model that I talked about earlier, it actually attempts to be adaptive, but eventual consistency only gives you this model. No updates occur for a long period of time, then everything will be consistent. This has been often called BASE. It stands for basically, it's a made up acronym as far as I know. It stands for basically available, soft state, and eventually consistent. It's a long name, some cooked up name. And the reason why it was called BASE is because there's a different model called ACID. We looked at it, we talked about it earlier, which is used in databases and storage systems and operating systems, and this is basically ACID. Okay. So what is I'll come to this. I've already discussed a bit about this. We'll come to you. We will talk a bit more about it. So basically, because this model was ACID, this model was called BASE, and this cooked up name for it. Okay. So in ACID, what is the issue here? You're talking about multiple transactions, and you want to ensure that either the transaction goes through or the transaction does not go through. Let's look at one example. Suppose I want to go someplace. I want to get a railway ticket booking, plus I want to get a hotel booking, and probably a ticket for some event that I'm interested in. So I'm interested in doing it only if I get the railway ticket / the hotel plus the ticket. Okay. So I'm talking about transactions in which you try to do all of them. If any one of them doesn't work out, you might want to back out of it. So the issue that I'm interested is either the transaction completes or doesn't complete. I don't want intermediate states where I have a hotel booking, but I don't have the train booking / the event booking. Okay, that doesn't work for me. So I want it to be either all of them to happen or none of them to happen. So some updates I'm making to some system, all the updates have to happen or none of them should happen. That is basically atomicity. Notice that this model atomicity is somewhat different from what people in operating systems would call it. In atomicity, as operating system people generally understand it, it means that I have two operations A and B, nobody comes in between. Okay, that's usually the model, that's what they usually call as atomicity. Whereas databases is a slightly different model because you're talking about applications here. So here what they are interested is not the fact that somebody has come in between. What they want to make sure is that either I did something or it's the same state as before. That's what atomicity is. The consistency. What is consistency here? It basically says that there is some model of how data in my system, there is some invariant that has to be satisfied. That invariant always has to be satisfied. Okay. So whatever any transaction does, it has to keep the invariant intact. If you are not able to keep the invariant intact, then you are not consistent. Now again, if you talk about a file system, nobody has told it how you should touch its data, how you should handle its data. There is no model. Therefore, file system does not have a model of consistency, whereas a database has a model of consistency because there is some schema and there is various other things, right, which tells you what has to be done. Okay. So the database has a consistency model. So it is not really, as a systems person, suppose you're building a system, this C is actually not part of the system definition. Okay. That's why file system does not worry about this at all. Okay. The only thing it worries about is its own model of its metadata. It has to be consistent. Okay. What is internal to it, that's all it bothers about. Okay. What is I? I is isolation. Isolation basically means that if you have multiple concurrent transactions, it should be, even if you are executing it concurrently, even if each of the transactions are reading and writing things concurrently, whatever be the effect of execution of all these concurrent transactions, it should be equivalent to some serial execution. That's what isolation is. That means that each transaction, it executes as if it was isolated from other transactions. Okay. It should have that, the equivalent behavior. That's what isolation is. Okay. And this is required also for file systems and databases. All these things are required for this. Okay. So the D part of it is a durability part. So D, what does it mean? It means that if I write something, it should, in spite of failures, crashes, panics in the system, whatever, right? When the system comes up again, whatever I wrote before the system went down, it should persist. So the D is the durable part of it. Of course, the D is the main concern in storage systems. So this is an important thing to be looked at. Okay. So essentially, when we look at certain systems, database systems especially, they have this ACID model, but this ACID model is too sometimes extreme or too difficult to handle. Okay. And therefore, you need some weaker models. As I mentioned earlier, there are real-time systems in which ACID doesn't make any sense. Okay. Because, as I mentioned earlier, you have air traffic controller systems where if some part of the system dies, you can't just say that I'm going to ensure that the system is, quote, completely consistent across all the parties. I need to take some real-time actions and I will tolerate certain failures and should proceed. I'll do basically what you might call as best effort delivery of the service that I can do. Okay. So ACID model is not meaningful in those kind of circumstances, or in circumstances in which the consistency notion is not itself clear to the party who is supposed to provide the model. Okay. As I mentioned earlier, the file system has no idea about consistency of the data. Nobody has told it. Okay. So there is no way it can do ACID the way it is mentioned here. Okay. But it can do ACID with its own data structures. Okay. Because it knows something about its own metadata and it can do all these things. Okay. So in a sense, you might see that the file system actually implements an equivalent ACID kind of thing for its own data, okay, but not for the application data. That's the difference between a file system and database. Okay. Now, this acid has originally was, for example, proposed by Lamson, and it was picked up by Gray, etc., in the database community, and it became famous there. And so the opposite acid is basically base. Okay. So whereas where you don't really guarantee the consistency until all the updates propagate through the system, okay, and then only you can say that the replicas will be consistent. Okay. So let's look at what Zookeeper does. Zookeeper also says something similar. The client view of the system is guaranteed to be up to date within a certain time bound. So, for example, in the Zookeeper model, you might keep information about which machines are up, which machines are down. Okay. Now, it's possible that within that time bound, okay, if you wait long enough, then it will all be consistent. But if it is much before that, it may be that some machine is thought to be alive when it is dead, and vice versa. It's possible. And this can create lots of complexities in real systems, and that's why, as I mentioned earlier, there is something called group communication systems which attempts to solve this problem. We will take a look at it because some storage systems use group communication systems as a way to make the programming job in the kernel easier. Okay. Because when systems in when the certain parts of systems are in a slightly anomalous state, it's very difficult to program in that context. So you need some kind of infrastructure which shields you from this, and it can be a kernel infrastructure which can be used so that this is possible. So let us just look at in some detail with Zookeeper consistency model. This Zookeeper consistency model guarantees the following: sequential consistency. Updates from a client will be applied in order that they were sent. Okay. It's not the case that it will go in different orders. As I mentioned earlier, web does not have this property. That's why cricket scores, the cricket score need not be monotonic. It will show 365 and then suddenly it shows 360 later. It's possible. Okay. Atomicity. This is what we just discussed. Updates succeed or fail, no partial results. Single system image. A client will see the same view of the service regardless of the server that it connects from. Basically, as I mentioned to you earlier, Zookeeper is replicated so that it can scale with respect to number of clients, and also to make sure that if there is any failure, if there is a crash of the systems, some systems, then you don't lose all the information. So it's important that the client will see the same view of the service regardless of the server that it connects to. Again, this is also guaranteed by group communication systems. Group communication systems, they go through what is called views, and they ensure, of course, it cannot be done absolutely because, as I mentioned, FLP results will prevent it from it, but they try to ensure as far as possible that each client has the same view of the system, and all the messages that are sent and received, they go in a particular order. And so group communication system also give you some, they attempt to do the same thing. Reliability. Once an update has been applied, it will persist from then until a client overwrites the update. That means what they are trying to say is that if you write something, the bits will not rot. Okay? It's possible, right? For example, sometimes what happens is that on a disk, you write something and you read it after about 3 years. There is a small finite chance that it will develop what is called latent sector error. I think this happens although on CD-ROMs. It happens also for floppy drives, which probably nobody knows now, not nowadays, but happens in all those situations. In the case of CD-ROMs, it turns out that it happens because it uses certain organic polymers, and organic polymers degrade over a period of time. So because they degrade over a period of time, it can turn out that what was once a 1 or 0 can be indeterminate. Okay. It cannot be figured out. Basically, the signals that are picked up when the reader, CD-ROM reader, tries to read it, it doesn't give a clear 0 or 1. Okay. It's possible. Okay. So in a sense, if you have the reliability, that means that you have to be able to overcome all these kinds of issues. That means that somebody is actively scrubbing the information. What is scrubbing? It means that somebody is attempting to read it every so now and then, so that this kind of bit rot does not happen. Okay. Somebody has to be reading it every so often and writing it to some other place, and so keep the data alive in some sense. Okay. But the one which we are interested about is this part, timeliness. The client's view of the system is guaranteed to be up to date within a certain time bound. Okay. This is a critical thing. Okay. So again, this is basically what is called eventual consistency model. Eventual consistency model. Okay. The only big issue for us is that time bound is not mentioned. Okay. It depends on different. You have to know the system you are working with and come up with that particular time bound and then work with it. There is no automatic ways of figuring out what it is. So let us just summarize again some of the discussions so far. So there are two models, the acid versus base models. As I mentioned to you earlier, the reason why you have different models is because you have different domains in which you work. It could be the real-time systems domain, it could be the file system domain, database domain, and other kinds of domains. Each of them have their own particularities and issues they have to solve, so they will do it in different ways. So in acid, the issue is strong consistency, isolation, but availability is not seriously looked at, because availability has to be thrown out, precisely because if you want to have strong consistency, the FLP results comes in the way. Therefore, you cannot have strong availability and consistency. Okay. It turns out to be conservative. That means because of need for strong consistency, it will block, it will wait for some situations to become alright before it will proceed. So it's pessimistic. It assumes the worst has taken place, and it will keep waiting till everything seems okay, then it will proceed. Okay. Otherwise, you can also have nested transactions. Basically, so the top level transaction depends on what has happened to let us say sub transactions, and so there is some issues of the correctness of it based on the correctness of the sub transactions. And typically the system evolution, any system based on acid model has a slightly difficult system evolution, precisely because you have to specify what a consistency model is. So once you specify the consistency, what does it mean? It means you have to give it some invariants, and they have to be carefully specified. So anytime you add something or take out something, you have to again revisit consistency. Is this added this piece of stuff? Does it again, is my invariant still valid or invalid? I have to keep thinking about all these things, and turns out to be non-trivial. Okay. So where in the case of base, it's weak consistency, it's okay to provide stale data once in a while. It's not catastrophic. Okay. Or it may be that for reasons of progress in the system, you don't mind certain parties not responding in time. Okay, you just proceed. Okay. So the most important thing is availability. Again, as I mentioned earlier, it is required for some critical systems which need to make progress. You have to make progress, you have to just drop some issues. Okay, consistency being one of them. There is always best effort, and approximate answers are okay. Again, you can think about the following: if your car has stopped moving, you would like to somehow get it going somewhere or other. You don't really care about the most elegant way to do it or the most correct way of doing it. You just want to keep it going till you get to some place where it can get repaired. Same thing here. Okay. So base is basically that model. It is optimistic. Okay. It assumes that because you are being weakly consistent, there are certainly going to be problems, but it's optimistic in the sense that you hope that somehow it can be fixed later. Okay. It's not catastrophic. Things diverge in values. Somehow I'm able to reconcile them later. That's why it's optimistic. Okay. It's aggressive in terms of moving forward. That's what it means. Okay. So it's got an easier system evolution because it doesn't have very strong notions of invariant properties, and that is quite true for most large systems. If I'm talking about a large system, there is nobody comes and says that this is the invariant that has to be followed. Suppose you take a look at the case of some major problems that we face in the world right now, right? There is question of some parties which want to blow up some places, right? There's no such says that you cannot, that all buildings have to be or some such thing, right? So there is no such invariant available that has to be satisfied. Okay. So, therefore, it is possible, because there is no invariant, you can add things and remove things without worrying about destroying some invariants. Okay. Of course, it may not function the way you want it, but it allows you to make progress locally. Okay. So, it is may not be the best, but it allows progress. That is most important thing. Okay. So, we will try to see this in connection with, let us try to understand this problem a bit more in some depth. So, we will look at an abstract problem related to consistency. This is basically the commit or consensus protocols. Okay. So, basically there is this problem called atomic commitment, let's call it AC and consensus. I will come to the differences soon. First, let us look at atomic commitment. Okay. So, what is it? How is it defined? Basically, you have set of processes and they either have to vote yes or no, and before they decide yes or no, they could be in some undefined state, but they have to move to yes or no. Okay. Now, what is the thing that we are thinking about? They all agree on, basically it is a simpler problem. What we are saying is we are just talking about two decisions, yes or no. Okay. You can, from this you can actually construct other kinds of problems, like for example, deciding on a particular value. For example, should the value be 7, 8 or 100, whatever. Okay. And but right now we are going to talk about binary, which is yes or no. Okay. So, what are the issues, what are the kinds of properties that you may want to have for atomic commitment? Okay. The first obvious thing is no two processes reach different decisions. Either everybody has agreed to yes or everybody agrees to no. Okay. One of these things. Okay. So, this is fairly straightforward. Commit is decided only if all votes are yes. Okay. So, this is one you might call axiom. Commit is decided only if all votes are yes. Notice that I am not saying commit is decided if and only if all votes are yes. That is the reverse direction is not interesting or useful. Okay. If there are no failures and all votes are yes, then all processes decide to commit. Okay. Then there is another one, AC4. If all existing failures are repaired and no new failures occur for a sufficiently long period of time, then all processes will reach a decision. Okay. Now, you can see that all of these things are independent. You can have any combination of these things. Okay. For example, what we are saying is that we are not saying if not, what happens if some of the votes are not yes. Okay. We leave that situation open, we do not say anything about that. Okay. Whereas, if it is yes, that means everybody has agreed. Okay. So, the other thing we are not saying here is, are the processes correct, or the processes can fail in some strange ways, what is called Byzantine ways. That means, they are saying yes, but actually they mean no, etc. Okay, those kinds. We are not talking about failures of that type. So, the only thing that we are talking about at the best are if they are what are called stop failures. That means that if they fail, they have accumulated some state which can be looked at when they come up again. Okay. That is all we are talking about. Okay. There is no Byzantine failures here, okay, or what I call benign failures. Okay. Now, ideally I want this no blocking property, all correct processes reach a decision. Now, it turns out, as we discussed earlier, the two generals paradox, that problem, it makes this particular problem unrealizable. That is, one cannot come up with this particular situation, that is all correct process reach a decision, because it is always possible, because I am saying that it is decided only if all votes are yes. Therefore, if some parties have decided S, but before they can vote S, if they die, right, then you are in an indeterminate state. Okay. So, and this kind of models are appropriate for databases and file systems, because for file systems with respect to metadata consistency, and for databases for application level consistency, okay, because that's something important and it has to be handled. Okay. So, using this kind of atomic commitment protocol, you can construct more complex ones which agree on a particular value, or which file has to be, which file needs to flush its data to the disk or whatever. Okay, you can construct all those things. Okay. So you can see that there is various assumptions made, and this, for example, no new failures occur for a sufficient long period of time. This looks similar to the eventual consistency model we talked about. Okay. There is also this something called consensus problem. Okay. So, in the previous case, here we are not saying anything about what the faulty processes are doing. The faulty processes also have to say yes, okay, which is a bit of a peculiar thing, whereas in the consensus problem we can exclude faulty processes. Okay. So, basically in some sense the assumption is that the faulty processes, they basically crash and then come up again somehow. That is the assumption made in this model. Okay. Whereas in the case of consensus, faulty processes can do arbitrary things, they can be Byzantine. Okay. So, that is why we are carefully delimiting how we make our minds on consensus. All non-faulty processes reach the same decision. Okay. Again, specifically saying non-faulty process. Whereas in the case of the atomic commitment, we do not talk about non-faulty process. Okay. There is also a validity issue. If all non-faulty processes votes are S, they will all decide to commit. If all non-faulty processes votes are no, they will all decide to abort. Okay. So, this is validity. Okay. Now, one thing that one should mention already is that there are some fundamental problems here itself. It turns out to detect if a process is faulty or not itself is not feasible. Again, that comes back to FLP again. Okay. So, these things are in principle infeasible. A and V together are infeasible. You need to have some weaker models. One weak model is if there are no failures, V holds. That means that, of course, there are no failures, therefore you do not have to think about non-faulty processes. Therefore, this is appropriate. Then there is also a very weak validity. Both commit and abort are possible decision values. There is an execution in which correct processes decide to commit, and execution in which correct processes decide to abort. So, there is a lot more latitude here. Here we mentioned that if all non-faulty processes are S, then they have to decide to commit. Here it is possible that they also, in spite of that, they can do an abort. Okay, it is like even more weaker. The only thing that is being said here is all agree on either commit or abort. That is all they say. Okay. Whereas this one is stronger. Okay. But it turns out that you can come up with varieties of weaker kinds of problems, starting with consensus problem, which is a stronger one, then weak consensus and very weak consensus. Very weak consensus, for example, is basically agreement and the very weak validity. Okay. So, as I mentioned earlier, this consensus problem is used in the real-time systems community. This air traffic control kind of situations, they actually try to follow this kind of model. The idea here is that when some part of the system dies, you are not going to wait for it to come up. In the case of databases or file systems, usually when they do some operations, they have some persistent storage which has to be looked at when they come up again. That is, when they reboot again, there is already some state that has been accumulated in the previous life, you might say, and that information has to be used to guide the new booting system. Okay. So, therefore, it can take much longer period of time and so it makes sense for you to go for this model, commit kind of models, for databases and file systems. Whereas for those real-time kind of systems, consensus is a lot more sensible, because you're not going to be you're going to be have to react to something quickly, and you can't wait for systems to reboot and use the old state, persistent state, to guide what has to happen next. Okay. So if you look at atomic commitment and consensus, you'll see that the differences are because what happens with respect to faulty process. As I mentioned earlier, in the case of atomic commitment, even faulty process have to say yes for commitment, okay, whereas that is not really necessary for consensus. Okay. So it turns out that atomic commitment, as I mentioned earlier, is attainable only under assumption that process failures are benign, and it is not valid for Byzantine failures. We can quickly look at and convince ourselves that certain things imply something else. It turns out that atomic commitment has conditions much stronger than weak validity, and various results, theoretical results, have been shown about the weak validity model for consensus. And essentially what we can say is that everything that has been proved in that context is actually going to limit commitment also. Okay. So let us just look at one or two things quickly and see what the issue is. Okay. Now if I look at the conditions 2, 3, 4 imply weak validity. What is 2, 3, 4? Commit is decided only if all votes are yes. If there are no failures and all votes are yes, then all processes decide to commit. So these things, if all existing failures are repaired and no new failures occur for a sufficiently long period of time, then all processes will reach a decision. You can see that this is connected with the weak validity. What is it saying? It's saying there are no failures, then V holds. And so if there are no failures, then you can say that if all processes, like now all of them are correct or votes are yes, they will decide all commit. And if all processes which are correct now because there are no failures or no, they will all decide to abort. Okay. So now the reason why 4 is included is because if you have some failures but no new failures occur for some long period of time, then again this issue is similar to what is there in the condition here. Therefore, you can show that 2, 3, 4 essentially imply weak validity. The reverse is not true because, as I said earlier, in the case of here, even faulty processes have to agree on S, which is not required in the case of consensus. There is also another axiom you can put, so that, for example, I had this condition in the case of commit protocols about this part, okay, and it is not there for consensus. So if I want to make both of them similar, then basically I can add this part. If I have this part, then I can essentially get the agreement part of it, okay, because then I have added this the fact that things stabilize, right, is available now for the consensus also. Therefore, it is possible for me to now say that AC1, AC4 and the fact that things stabilize after some period of time, they imply agreement. Okay. So basically, the attempt here is basically to show that the various conditions, various communities are assuming some conditions are stronger, some conditions are weaker. As I mentioned earlier, the storage systems or database community, they have much stronger requirements compared to the other parties who are assume a weaker model, because for them progress is far more important than, again, if you look at the web community, same situation, for them progress or availability is far more important than complete consistency. So they have much more weaker models. Okay. So that explains why You can use the web, which is highly available, but it can give you some incorrect information, and if you try to make it consistent, then you have situations where it's not possible. Okay. So what we'll do next is to look at, in the next class, we'll look at some commit protocols, what is called the two-phase commit protocol, and then we'll look at its natural progression to three-phase commit protocol, and then we'll go to other models like Paxos, and then get on to how some of these things impact the design of large-scale storage systems. Thank you.